Hello, my name is Mason Randall, and I am joined by Kakeru Kobayashi and William Duncan. This course is instructed by David McNair, and the TAs for the lab section are Alana Homa and Nicholas Miller. This is the IC Engines progress presentation for Team 4. The link to this presentation will be found at the bottom of this slide once the video is uploaded. Generative Energy Systems Incorporated has requested the assistance of Burdell Inc. engineers to determine system parameters and controls for their new generator that is based on a modular internal combustion engine. This particular engine is unique in that it can be operated from both compressed air as well as a propane fuel source. The engine is connected to a 48-volt regenerative motor, which allows the engine to start. This motor can also be turned by the engine to generate energy for storing in an attached battery pack. Testing and analysis will be performed over 3 weeks, so this presentation is to discuss the results of the first week of data collection and to outline the plan and expectations for the next 2 weeks of lab sessions. The first week of data collection focuses on the actual mechanical properties of the IC engine, the relationship between piston position and shaft angle, the friction acting on the flywheel, and the inertia being created by the flywheel are all concepts that are evaluated in the first week of testing. These results will be discussed specifically in the presentation. The next 2 weeks shift focus to the engine's fluid properties, and the plan for future data collection will be detailed in later slides. The particular system that the team is working with has been instrumented with an encoder to detect engine and motor shaft position, and a force transducer in order to detect the torque being experienced by the motor. Specifically, this experiment requires an optical encoder, an electrical mass scale, digital calipers for precise measurements, and an Elvis board. Firstly, the physical dimensions of the engine are measured. This includes the cylinder dimensions of bore diameter, top dead center, and bottom dead center measurements. Following this process, the offset between the encoder reading and top dead center was evaluated to avoid errors in future calculations. Motor torque versus angular position data and piston location versus angular position data was obtained for 3 steady-state angular velocities ranging from low to high speed. 0.3, 0.6, and 0.9 voltage inputs were used and are recommended as a starting point for data collection. Upon completing the analyzation stage for each of the 3 voltage inputs, the measurements are to be repeated with only one flywheel attached to the engine so that the system can be analyzed with less mass influencing the engine. The data will be used to construct a mathematical model based on the work kinetic energy theorem. The work done by the motor on the engine will be used to complete this mathematical model. Specifically, the frictional torque and flywheel moment of inertia are the main calculation goals during this phase of data gathering. These are several of the assumptions that are made in order to receive the calculations that are detailed in this presentation. Firstly, known weights were used to average torque from the force transducer, and these values were integrated over angular position to determine the work of the motor. To calculate the work due to friction, the work caused by air was assumed to be negligible when the engine had the head removed. The system was also assumed to be adiabatic, meaning that energy lost to heat transfer is negligible, and the work due to the piston is considered inconsequential compared to the friction work. Although the angular velocity is available to measure, the flywheel moment of inertia is not as easy to determine. By using the same assumptions as mentioned before, the acceleration of the motor can be reviewed to calculate inertia. Additionally, air pressure will be considered constant, or isobaric, in order to calculate the work due to air. In terms of uncertainty, K equals 1 coverage factor is used, and digital readings use the standard uncertainty equations.
With the head of the motor removed, it was decided to go ahead and take measurements of the engine's bore. While the height uncertainty above top dead center and bottom dead center had similar uncertainty, the uncertainty of the bore diameter was much larger. This was due to the fact that it was difficult to align the calipers with the hole's diameter. Moving now into more of the motor's response. The motor received 3 different input voltages of 0.3, 0.6, and 0.9 volts respectively. The overall trend of each motor's response is pretty similar, as the torque was very large at the beginning and steadily decreases until it reaches the steady state torque. Where things seem to differ is the initial torque value of the motor seems to increase as the input voltage increases. Diving a little bit deeper, the results show that the torque from friction appears to increase with the increases in steady-state rotations per minute, or RPM. This suggests that the friction of the flywheel behaves in a similar manner to that of a Newtonian fluid, as the friction increases from 1.61 newton meters to 1.80 newton meters with the increase in RPM. It also is interesting to note that the calculated values from the moment of inertia of this section do not match the theoretical model. This is because the calculated moment of inertia also includes the inertia of several internal motor components that are not being accounted for in the theoretical model. To further investigate the discrepancies in moment of inertia, only one flywheel was placed on the motor this time, and the previous tests were repeated. Comparing the differences in motor response for the varying number of flywheels, the motor with one flywheel accelerated to steady state around 1,000 radians earlier than the motor with 4 flywheels. This makes intuitive sense, as lowering the moment of inertia is essentially lowering its resistance to being radially accelerated. Another interesting calculation was the frictional torque values remained almost unchanged, with the values being within one standard deviation of the other. Following the Newtonian friction model, this makes perfect sense as the steady state RPM only changed by around 9 rotations per minute. By subtracting the calculated moment of inertia for one flywheel from that of 4, it should more closely match the theoretical values. While the discrepancy between the theoretical was decreased to 0.0037 kilograms per meter squared, there is still a 31% error between that and the theoretical value. Moving to an input voltage of 0.6 volts, the data follows a similar trend as before. What is interesting is that the frictional torque seemed to barely increase when the steady state RPM was lowered. This result does not fully match with the Newtonian friction model, but this could easily be explained with the measurement uncertainty. This is because the uncertainty of the measured torque from one flywheel study is larger than the original torque calculation. With the discrepancy from the frictional torque, the discrepancy in the moment of inertia also increases to 32%. Finally, moving to an input voltage of 0.3 volts, the data continues to follow the previous trends. From both studies, the steady-state RPM is relatively unchanging, and as a result, the torque due to friction from both studies is also relatively unchanging, at 1.6 newton meters. There continues to be a discrepancy between the theoretical and the calculated moment of inertia. While this discrepancy could be caused by the measured error of the system, the continuous trend of error suggests that there is some outside factor causing the error.
We calculated the work of motor, work of friction, and moment of inertia of flywheel in week 1. The angular velocity and the work of motor are measured directly from the system, so the only unknown quantity is the work of air. It is calculated by replacing the engine head in the next step. After comparing the model and experimental work of air, the discrepancy between them is used to determine how well the model matches the data. Conclusion: we calculate the cylinder dimensions that will be used to calculate the volume of compression and expansion of the engine in week 2. We also calibrated the force transducer to convert the input voltage to torque, and based on the measured data, work of motor, work of friction, and moment of inertia were calculated. It turned out there were 24 to 32% discrepancy between the theoretical and experimental moment of inertia that could be caused of outside of effect of the system. Again, the frictional torque changes with engine RPM, which can be expressed as Newtonian friction model, and removing flywheel leads the increasing of the time to reach steady state. Lastly, calculate the moment of inertia, increase the motor component inside of IC engine besides the flywheel. Thank you for listening. We would like to take any questions.